Recall in the first video that we did on heteroscedasticity, where we tested the Goldfield-Quant test, we noticed that we were having a linear relationship between the independent variable and the outcome variable, and eventually we also saw that the variation in the error term increased as the independent variable increased. And we noticed that we could replicate that into a relationship between the variation of the error term and the independent variable. But what if this relationship does not happen linearly? So what if we have a quadratic or any other type of relationship between the two variables? So let's see what this test is going to help us to do, because we have a test for that. It's called the Y test for heteroscedasticity, and we're going to do it here on a graph. So this one, what if we have a quadratic relationship between one of the independent variables, let's call that x1, and the variation of the error term? So it would go like that. It would fall and then rise. Well, notice, if we plot that into our regression line, we would have very many variables to test for. We would have to have a long test, because we have the linear effect of x1 and x2, and I made it just until x2 for the sake of not making it too long, but just to prove the point that it becomes very long. So over here we have included only two independent variables, and also the quadratic term and the multiplicative effect of those terms. But if we also have x3, then we should also have x3 here, and then x1 times x2 times x3. So long story short, we would have very many variables in the model, so the test is becoming very long. We have a lot of degrees of freedom to take into account, and that's just becoming a bit hard to do. So what's a wiser thing to do is to condense this relationship. How can we condense it? Well, we could write it in the following way. We could have the relationship between the variation of the error term, I wanted to say u square, I wrote u2, u square, based on the following. We have still a constant term, so we have, let's call that with different letters now, gamma 0 plus gamma 1 times the regressed value of y, so gamma 1 times y hat plus gamma 2 times y hat to the power of 2. So we would have gamma 2 times y hat to the power of 2. Why do we include y hat to the power of 2? Well, recall, y hat, let's assume y hat is gonna be alpha plus beta 1 x1 plus beta 2 x2. Well, notice, if we take this thing to the power of 2, what happens with the math there? Well, when we expand the brackets, so this thing to the power of 2, we're going to have alpha squared plus beta 1, and we will have probably to the power of 2 x1 to the power of 2, and then we will also have beta 2 x2 squared. We'll have something related with x1 and x2 when we multiply them together. So we'll have beta 1, beta 2, x1, x2, and we'll have some other terms when we expand this bracket. I'm not going to do it completely, but just to prove the point. What I'm trying to show here is that these terms that we are noticing in the first regression line that was really long are included in this condensed version over here. And that's what we're doing. That's why we are doing it. And now what we want to do is we want to test for a joint effect of delta 1 and delta 2, because we want to know whether there is a relationship between the variation of the error term and the predicted values, because the predicted values include the independent variables x1 and x2. So implicitly we're still testing for the relationship between the independent variables and the variation of the error term. But what we're doing right now, we are also including the quadratic term, and it could be a cubic effect as well, depending on the regression line. So to not put all the variables in such a long line, we're making it more condensed. We're testing for the joint effect. So the null hypothesis is that delta 1 equals to 0 and delta 2 equals to 0. Or the alternative is going to be that at least one of them differs than 0. So at least one delta differs than 0. And in this case, we are testing still for heteroscedasticity, but taking into account also quadratic effects and other polynomial effects. That's the idea. That's the last test that we can have for heteroscedasticity. Hope this all makes sense, and we are done.